Hello, good evening everyone. Welcome to Week 11 problem solving sessions for Analog Electronic Circuits course. And in this week, so we are one less to the final week, and this week we'll be talking about feedbacks. So let us understand what are feedbacks. So, what do we understand by the term feedback? When we listen to feedback, in general, what do we mean by feedbacks? So, basically, when somebody is saying something or presenting something, then you present your views based on their presentations, right? Or their talks, or anything. If somebody is talking to you in any manner or communicating to you in any manner, you uh, you present a feedback to them. Hi Himali. So I just started the session. So this session will be talking about feedbacks. Am I audible to you? Am I audible clearly? Hello?
Yeah, you're audible.
Okay. Let's begin. So I was talking about feedbacks. So what do we understand by feedbacks in general? Like not talking about electrical terms, but just in general, what do we understand by feedbacks? So what are your views? Like what is feedback? Let's make it an interactive session. You can unmute yourself simply. Hello? Hello? Himali, are you there?
Hello, yeah,
Yeah.
giving a feedback, like about an output, we give a feedback. How is it proper or not?
Yeah. So, in general, when we say if somebody is communicating to you in any manner, let's say it is a presentation form or just in a normal conversation, also, whatever you get from that communication, you give them a feedback or you give your response towards their communication, right? That is basically feedback. So, likewise, in electrical terms or in devices terms, we also have feedbacks. Now, what is the importance of feedback? Like, what is the basic use of feedback? When we say feedback, what is it basically? Why we need feedbacks? Is it advantageous to have feedbacks or is it disadvantageous?
Yeah, it's advantageous to have feedback because we can if there's any discrepancy in the output, we can change it appropriately.
Yes,
The
and
input.
in general, also when you give feedbacks, it's just to improve that person, right? If I am, let's say, I'm presenting something, or I'm, let's say, teaching to you, I always get your feedbacks like, how was it? Like, what did you understand? Whether you understand or not. So, what it tells me from your feedback that whether you understood it or not. So, it is for me to improve as well, right? So,
Yeah.
feedbacks are always advantageous. So, in devices terms, also, we provide feedbacks. Now, when we talk about feedbacks, so it is something, let's say we are giving an input, and this is, let's say, a circuit, and we have an output, right? Now, what we do, we just feed this output with some factor to the input. This can vary from 0 to 1, right? We can completely feed the output or we can simply remove the output. So, this beta factor, which is generally the amplitude which we are actually feeding to of the output to input, is between 0 to 1. Now when we talk about feedbacks, so there are two types of feedbacks. One is positive and other is negative. So what do we mean by positive feedback and what do we mean by negative feedback? So just let's see in at this particular point here, if we have input and let's say at x, so at x, if we are getting input plus beta times out, in plus beta times out, then this refers to positive feedback. And if x is in minus beta times out, then it is negative feedback, which basically means whether your feedback is additive to the input or subtractive to the input. Whether you are taking something out of your input or you are feeding something into the input or adding into the input makes it positive or negative feedback. Now, coming to electrical circuits, these two feedbacks are used. Both the feedbacks are useful and they both have their advantages and disadvantages. Okay. Now coming to,
Coming to,
sorry, yeah,
sorry, yeah. Actually, I had a doubt on beta. Like,
yeah.
beta is just a factor, right? What exactly it is it?
So
So
basically,
basically,
I'm getting a feedback. Uh, Wait, I'm getting feedback from somewhere. Hmm. How can I completely mute this? Okay, so basically, beta is it is a factor which you are using to feed your output. So it's just a amplification factor, you can say. So it is not amplifying because you will not give beta more than one. So you can completely feed your output or you'll give a factor of your output, right? So it is between 0 to 1. So either if it is, let's say the beta factor is 0, that means you are not giving any feedback. And if it is 1, that beta factor is 1, that means your output is being completely fed to input. Now you cannot go beyond 1, right? Why? Because output से ज़्यादा क्या होगा? What you will not like add something to output, right? You have got the output that is there. Now you cannot add something into the output and give it as a feedback. That will not work because
huh.
we want to actually check how we are getting the output, what kind of output it is, whether it is correct or not. Even this is we are talking about circuits, but in general also you might have seen in signals and all feedbacks are very important to error check when we
Yeah.
say like feedbacks or in general like back propagation, all these things are basically feedbacks only. We cross check and for errors, to detect errors and to rectify your circuits, and in mostly in adaptive circuits and all, in ML and all these AI based adaptive circuits, the feedbacks are very important. So the maximum that you can give to the feedback is your output, and the
Okay.
minimum is you can remove, like you can just remove the feedback. Because let's say if your circuit is strained, I'm going a bit diverted. I'll talk in terms of, let's say there is a uh, machine learning based system. Okay, so
Okay.
you have a circuit, you are trying to train that circuit. Okay, you had certain samples, you had datas, you had outputs corresponding to them. Now you are designing that circuit so that your output for the input set, you should get that particular output which you have in the data set, right? Now you are developing this circuit. So you have made first set of circuit. Now what you will do, you will get some output. You'll cross check that output with your database, like the output of the database, right? And you will get that error. And that error is again fed into input. So what we are doing actually manually, it can be done using feedbacks also. So while using this feedback circuit, so it will automatically check that error and simply it will feed it into the input and it will improve your circuit. So that's how all these adaptive circuits and even the circuit training or the system training that happens in ML AI, that works on this principle. So that's why we say feedbacks are very important. So
Yeah.
okay, I hope this makes you understand something. So did I
Yeah,
confuse you
yeah.
even more?
No,
No, right?
actually, it made sense, but I came
Okay,
across this one problem in my prescribed textbook from my college.
okay,
They just gave a amplifier and they gave a negative feedback itself, but they
yes,
were asking to find an expression for the feedback. And I'll
okay,
just like if there's any way I can just show you the problem, but I didn't understand how did they get the expression. So that was my doubt.
okay. So maybe we'll finish this session and afterwards we'll discuss that problem as well. Is
Yeah,
it
sure.
fine for you? Okay. So moving ahead, yeah. So I was saying there are two types of feedbacks in our electrical systems, that is positive and negative feedback. Now the thing is where what type of feedback is used, like what is the application of positive feedback and what is the application of negative feedback. So for that, what we need to understand is, see, if you give, let's say, a amount of input you'll get a output as, let's say if this is input, your circuit has a gain of G. So your output is, if I'm giving X as my input, my output will be Vx. Let's say it is a linear system. So it will simply give me G times of X, right? Now if it is a positive feedback system, that means I'll have X plus beta times of out, right? So what will be my new output? It will be G times of X plus beta out, right? So here if you observe, so earlier it was X which became Gx. Now my output has increased. Can you see that? Now
Yeah,
if
yeah.
I say, if it is a negative feedback, that means X minus beta times out. So my output is X minus beta out into G. Now from Gx it has reduced. So it is very clear that when we apply a positive feedback, my output will start to increase. Whereas when I apply a negative feedback, my output will actually reduce. Okay. So based
Okay.
on these principles, now it is like these feedbacks are used for their advantages. For example, where we use negative feedback. So the best example that we have is an amplifier, or even if I be very specific, like we use feedbacks in normal amplifiers also, but the best example is an op-amp. Why do I say op-amp for negative feedback? That is because if you observe very carefully how your V in versus V out curve for an op-amp looks like. So for an ideal op-amp, it is actually like this. So the function is actually like this, and this is for ideal op-amp, which is for very very small value also it will reach its saturation value, Vsat and minus Vsat, right? And if it is a ideal, if it is a practical op-amp, so it will have a slight slope, but ultimately it will saturate. But this range of inputs that you can give actually in a op-amp are very small. This input range is very very small. So in this small range, even noise has very small inputs, right? Like noise has very small magnitude. So even
Yeah.
noise will be amplified. And for any signal which goes beyond this range, it will be always a saturated output. So you will not be able to actually see the operation of your op-amp as an amplifier for which you actually want to use that op-amp. Op-amp is an operational amplifier, right? So you want to see that working as an amplifier. But for each and every signal that you apply, it simply goes to saturation. So you are unable to get that amplification operation out of this op-amp. So what we do, we basically provide a negative feedback. With this, what it will do, it will actually extend your input range. And in this particular range, after this range, you will see the saturation. So that is the basic idea behind using this negative feedback. Okay, beyond this range, it will saturate. So this is after negative feedback.
You just told that, like
Yeah.
negative feedback reduces the output
Yes.
somehow less
Yes.
than the positive one.
Yes.
So how is it exactly extending it in the case of the op amp?
So, see, so let's say if op-amp had a ideal gain of G. Now,
Yeah.
after your feedback, so after negative feedback, what it will do is it will actually reduce your gain. So gain will becomes 1 times of 1 plus beta times, like it will reduce by 1 plus beta times. Now for let's say for this amount, like X input you were getting your like for X you had your V out as Vsat, right? This is
Mm-hmm.
because it will actually be G times of X. So
Okay.
you know this was like G times of X gives you Vsat. Now going from this perspective, if we move ahead, so I know that V of X is actually Vsat. But now my G dash has reduced. It has become G plus 1 by beta, right?
Yeah.
Now for it to go to G, I can use x plus extra input, right? X plus delta I can have to get my G dash equal to G,
Hmm.
because it is like 1 plus beta times I can have, no? 1
Yeah.
plus beta into 1 plus beta times of x. So this 1 plus beta times x, so this was input. So you can, from here you can clearly observe that my input range has increased.
Yeah.
Makes sense?
Yeah. Yeah.
So since my input range has increased, so I can give a large range of inputs and still my op-amp will work as an amplifier and it will not saturate. Otherwise, what would have happened? So for this particular case, it is x1 plus beta. The range has become from x minus x2, actually minus x1 plus beta to x1 plus beta,
Hmm.
right? So it is like 2 times of 1 plus beta. That factor has increased. Earlier it was only 2x. Now it is 2 times of x1 plus beta. So with that, actually we have increased the range of inputs. Like you can give a large range of inputs. And also for small ranges, if you observe very carefully, so noise has very small amplitudes. Like noise is so noise. What do we understand by noise? It is a high frequency signal, and generally it has very small amplitude. So
Hmm.
if you see very carefully, after we have extended our range of inputs, we've actually reduced the gain. So what it will do, it will actually reduce the gain for my noise also. Earlier, if there was an ideal op-amp, but due to its high gain, even the noise was getting amplified by that amount. But now the noise can be controlled. One thing is that. Secondly, you will be able to give a large range of inputs and you will get a large range of outputs for that, and your amplifier will work just fine. It will not go into saturation, so you can clearly get your amplification property out of your op-amp. So that's
Okay.
why we go for negative feedback in case of op-amps or in case of amplifiers, to improve the amplifiers and to improve their range, like the range of inputs. And it also changes the properties, like input resistance, output resistance. So if you would have gone through the lectures carefully of this week, you would have found that it was like explained very beautifully using the circuits, that how actually things change when we introduce feedbacks into our circuits. So yeah, this is about negative feedback. Now, when we talk about positive feedback, so there are circuits which use positive feedback also. So, do you know any circuit where positive feedback is used?
Oscillators.
Yes, oscillator. So, positive feedback, what it does is actually, in case of negative feedback, if I talk just from signals perspective to give you an idea, then. Mm, yeah. So, talking from signals perspective again, if say this is my signal, so actually negative feedback, say it will actually reduce my signal, whereas this is negative. But when it is like a positive feedback system, so it will actually increase my amplitude, right? So gain actually increases. So earlier, if the gain was G, it will become G by 1 by beta for let's say negative case, and it is G by 1 minus beta for the positive case. So it will basically increase the uh, gain.
Hmm.
So what happens is, in case of oscillators, acha, first of all, in oscillators, do we give any input?
No.
No. So how we get the oscillations out of our oscillator?
The output of the ladder is given to the amplifier. In turn, the output of the amplifier is given to the RC ladder in case of RC oscillators.
But is there any input signal involved? That is what I'm asking in case of oscillator.
No.
No, but so where are we getting that output signal from? We get a beautiful sine wave, right? Just if we talk about basic sinusoidal oscillators, we get beautiful sine waves out of the oscillator. But do we provide any type of sine? So when we see, when we are talking about amplifiers, we give them sinusoidal signals and we get the amplified version of sinusoids. That is amplifier. But when we talk about oscillator, we don't give any input, but we are getting a sinusoidal output, a very
Yeah.
beautiful sine wave. So where does that come from?
I'm not sure how we get that, but I'm like, we adjust the R and C accordingly so that we get an appropriate sine wave is what
So,
I.
yeah, so actually what happens is we know that oscillator is a positive signal, right? Well, like positive feedback circuit. So
Yeah.
even a small signal, a small trigger can start that feedback and it will blow the feedback again and again. So
Yeah.
when there is a small signal, it will first positively increase the amplitude, like it will amplify it, then it will be again positively fed into the input. So this positive feedback input will again be amplified twice, so square times. Then it will be again fed up. So it will continuously feed that input until it comes to a resonant state. And
Hmm.
that's where we get a stable sine wave. Let's say if we are talking about a sinusoidal input or sinusoidal oscillator. So that small trigger is actually sometimes the noise that we get,
Noise. Yeah.
the thermal noise that we get. So that basic thermal noise actually gets amplified multiple times in a positive feedback, and finally we get that resonant state where it stabilizes itself and we get that sine wave, that beautiful sine wave.
Yeah,
And
that's nice, but can we always count on this thermal noise? Like maybe if we are using it at an appropriate temperature, we might not get a noise, right?
see, we always use our devices on room temperatures, right? So we'll always have thermal noise present. And we don't generally, we see, normally whenever we are using our devices, they are always in room temperature, anywhere if we go, in general, normal areas. Yeah, I can say that thermal noise magnitude will change with temperature. That is known to us. But the noise will always be present. And even there are noises because of mismatches in the devices, or there are these type of noises which comes due to fabrication thing, or let's say there was some noise in actually the supply voltage, that VDD that we apply to the circuits. There was some noise, so that
Okay.
small noise can also trigger your circuit, and it will start and it gets into that positive feedback loop, and ultimately you'll get the sine wave. So that is why we say that positive feedback is not used, because there is no control to it. Like we cannot control the positive feedback.
Hmm.
When we have a negative feedback, we can actually control things. So when you want to have a controlled operation, we always go for negative feedback. So that's why in case of amplifiers, we have many constraints that we need to meet, right? We have swing, we have like gain that we need to meet, and all these bandwidth and all these factors need to be met, and we need to be closely controlled. So that's why for that close control, we always go for a negative feedback. So you'll never find an amplifier with a positive feedback. That is one of the major reasons why we go for negative feedback. But in case of oscillators, we don't have we don't have that much of a control in case of the amplifiers. It basically provides you a sine wave, and your frequency will be maintained using R and C values, but you cannot actually control how you are getting the sine wave. So it is mostly uncontrolled operation. So that's why it is very difficult to get a controlled operation out of positive feedback. So if you want to have anything in control, you need to go for negative feedback. So this is the basic idea that we have from positive and negative feedbacks. Hope this is clear. Uh, if you don't understand, just please ask. If I don't make any sense, or at some point you feel that something you are unable to understand, just feel free to ask. So
No, I'm following you so far.
yeah, yeah. Okay, so we have seen positive and negative feedback till now. Now we also understood that okay, if we have amplifiers, they must be negative feedback.
Hmm.
This is also clear to us. That means if there is an amplifier, say A, with the input and output, so that output will be fed with some factor beta to the input, and here it is actually negative.
Earlier, you mentioned the formula, right? Like A by 1 plus beta. Isn't that A by 1 plus A beta?
Yeah, so I was writing in general, like it is, if you go to exact formula, it is 1 plus a beta. Like in general, it reduces by 1 by 1 plus some factor. So that's how I was mentioning. If you go for exact formula, it is 1 plus a beta.
Okay.
I was just mentioning in generic, like how it appears. But yeah. So till now we have found out that amplifiers are negative feedback, and they will have something like this, some circuit of this sort.
Hmm.
Now, since we are talking about electrical circuits, so what are the basic electrical signals that we have?
Sinusoidal square. Oh,
No, in terms of electrical signals are always currents and voltages,
oh yeah,
right?
yeah.
We always talk about currents and voltages. So based on these current and voltage combinations, we have four different types of amplifiers with us. So let's say first, if my input is current and my output is also current, then it is a current
Current.
amplifier.
Mhm.
Now second, if it is a voltage input with voltage output, it is a voltage amplifier. Now if it is a current input and voltage output, what type of amplifier is this?
Uh, Trans impedance amplifier.
Yes, it is trans impedance or trans resistance also we can say. It is trans impedance or trans resistance amplifier. And if it is just opposite, that is voltage input and current output, it is actually trans conductance,
Conductance.
conductance amplifier. Now, based on these inputs or output, like what type of input you are applying and what type of output you are taking, your circuit, so when there is a circuit, you will have some input resistance, some output resistance, right?
Hmm.
So these input output resistance values will actually depend on what type of input you are applying and what type of output you are taking out of it. Now,
Hmm.
to make this very clear, first of all, when we talk about voltages, we always talk about Thevenin's equivalent circuit, which means if there is a voltage source, then your resistance with this voltage will always come in series with the source,
Hmm.
right? And if we have current, then we always use the Norton's equivalent form, which means always your current source will have its source resistance in parallel to the source.
Why
This
is that?
this is a convention that is always used for like voltage and current.
I
Well,
understand the voltage part because we'll have to get the appropriate voltage drop to give the appropriate input to the circuit.
hmm.
But what about current? Why do we need that?
So if you see, if you observe very carefully, these both are interchangeably almost same.
Hmm.
How? So when we have a voltage source, then a certain amount of current will flow through this, right?
Hmm.
And if we see, let's say if some circuit is there, let's say there is this circuit. So this circuit will get the same amount of current as that of this RTH resistance,
Hmm.
right? Now, in this case of current not in form, here we have current source. So current source will have certain voltage across it, right?
Yeah.
And if you observe very carefully, that same voltage actually appears across your R Norton resistance as well as your circuit.
Hmm.
So your current source will provide current. That current is being distributed across the circuit as well as your resistance. But
Hmm.
your voltage remains constant. Now,
Okay.
when we come to the voltage equivalent form, in that case, your voltage is actually distributed and current remains constant.
Hmm.
Do you understand? So, these two are actually very similar to one another. It's like, so when there is a current source, so for a current source, the voltage drop across that current source and even across all over the circuit which is there in parallel is always constant.
Yeah.
Voltage is not changing, it's the current that is changing.
Hmm.
Now, when we look into the voltage equivalent form, there the current is always constant because all the components are connected in series. It is the voltage drop that is changing across each circuit component,
Hmm.
right?
Yeah, yeah, I got
So that's how these two equivalents are designed,
it. Okay.
right?
Yeah.
So, do I make sense? Did you understand what I'm trying to say?
Yeah, yeah.
Yeah. So, that is the basic idea that for voltage we'll always use Thevenin equivalent form, and for current we'll always use the Norton's equivalent form. Now, when we have a voltage, let's say, see, if there is voltage in input, so there will be corresponding Rin with it. Or if
Hmm.
it is a current source, so it will have a corresponding Rn. And if that voltage is same at the output, we'll have corresponding Rout, and
Hmm.
similarly for current. So anywhere we will see that resistance either in input or in output, but the properties of those resistances will remain same. For voltage, it will have a certain behavior, and for current, it will have a certain behavior. For input, it will have certain behavior. For output, it will have certain behavior. Now, where does this come from? It comes from loading effect. Have you ever heard of loading effect?
Yeah, I'm actually confused about that. I wanted to ask about
Okay.
it.
So yeah, there is this term called loading effect. It appears to be very heavy term, like we don't know what it is, but it is something very, very simple. I'll explain you what it is. It is something very simple, and it's similar to uh, we can say voltage divider circuit. You have heard of voltage divider circuit, right?
Hmm. Yeah.
So let's say if there is a voltage source, okay, if there is a voltage source and there is, let's say, RTH, or let me write it as R source, okay, the resistance from the source, and there is your resistance across this. I'll call it as Rn. Let's say the voltage is connected to the input terminal of your amplifier. So amplifier ka there will be an input resistance and you will have your source resistance as well. Now, what do you basically want? You want that your voltage source, the voltage across the source Vs, should maximum drop across your Rn,
Hmm.
ideally. So if there was no Rs, if there was no Rs, then it would have completely dropped across Rn, right? But now due to this presence of Rs, what will happen? You will not see your complete voltage being transferred to Rn, but it is actually Vs minus delta.
Hmm.
So in case of a, now it is, if it is an amplifier, hmm, how should I show it? Okay, like VDD ground, and you will have again output. So you know that your amplifier basically amplifies whatever it sees in the input.
Hmm.
So if it has a factor of A, like as its gain, so at its output, it should actually give you A times Vs. But what it will give you currently, it will actually give you Vs minus delta. So you have
Okay.
lost on your signal. You didn't expect this. So you would say, okay, somewhere something has gone wrong. Did I like, so my amplifier was not designed perfectly? So the answer is no. It was not because of your amplifier, but it was because of your source. The type of source that you have applied and the corresponding source resistance that is coming into picture, right?
Okay.
And if we see, if we say like, what is this actual delta factor that is coming into picture? So if I write it as Vn, so it is actually Vn will be Rn times Rn minus, sorry, Rn plus Rs into Vs.
Hmm.
So this is what is actually coming across Rn, which is obviously less than Vs, right?
Yeah.
So this is actually loading factor, like loading effect that we talk about. If it comes into input, then it is that, and if it comes into output, then also it is considered.
So basically, we deliberately add a resistance to regulate the amount of current we
No,
want on the amplifier.
no. So what we actually do is we design our amplifier such that, because see, if there is a source, then the resistance coming from that source is always present. If I'm saying this Rs and I'm, let's say I'm using a battery, for example. So that
Hmm.
battery will have a certain resistance, certain source resistance, and you cannot manipulate that source resistance. It will always be present. So now what you can do to improve, so let's say if in this particular formula only, if you observe very carefully, if I make my Rs much lesser than Rn, so I can write Rn plus Rs almost equal to Rn, right?
Hmm.
Then my Vn will be almost equal to Vs,
Hmm. Yeah.
right? So I can get maximum voltage across my amplifier,
Hmm.
right?
Yeah.
So this is how we design our amplifiers so that it should avoid these loading effects.
So
Okay?
we want our amplifier to actually get what we are supplying, like
Yes,
completely.
yes. And also we want our load to get whatever is the output coming out of your amplifier. That means your amplifier should not eat any of your output signal. Whole of the output should transfer to the load. That is
Hmm.
why when we say there are constraints for input resistance, input impedance, output impedance, and till now you might have observed in all the amplifier circuits and in all the amplifier analysis, we always do the input impedance analysis, output impedance analysis. We find out how much is the actual input impedance, how much is it in the output impedance. Why is it very necessary? To avoid this loading effect. Is this clear? So
Yeah.
basically,
So
your amplifier should, so the basic idea is your amplifier should get all of its input, like whatever the input that you are supplying, your amplifier should get all that input in. And in your output, your amplifier should not consume any of your output signal, but it should transfer all of its output signal to the load.
hmm.
So that's why in case of voltage amplifier, when it is a voltage amplifier, in that case, we say that our input impedance Zn should be much higher. Zn much higher होने से क्या होगा? This condition will be satisfied, right? जो हम अभी देख रहे थे.
Hmm.
And we will,
Similarly, we should give a very high output resistance also to get a full output, right?
if you give a very high output amplifier, so high output resistance, so what will happen? It will actually drop all your output signal across your output resistance, and you will not get it out for the load, because after amplifier there is actually a load connected, and you
Mhm.
want your voltage or the amplified
Yeah, I mean
signal to
load.
transfer to the load, not to the amplifier.
Yeah, yeah, the load should be maximum, right?
Yes, the
Yeah.
load should be maximum, so Z out should be actually minimum.
Yeah,
Yeah.
okay.
Now, if this is the case for voltage, we know that current is opposite, right? Current follows the low resistance path. So that's why for a current signal, like current amplifier, your Zin should be as low as possible, and your Z out should be as high as possible. So current will follow a low resistance path. So when there is low resistance in your amplifier's input, the whole current will go through your amplifier. And when there is high impedance output, so it will actually avoid that path and it will go to the load, and the current will flow through the load. So that's
Mm.
why we want this for current amplifier. Now, if it is a okay. Now, if it is a transconductance amplifier, so transconductance means input is transconductance means input is voltage and output is current, right?
Yeah.
So here it will follow the convention of current. That means Z out should be much higher, but for input Z in should also be higher,
Mm.
right?
Mm.
And if it is trans resistance, that is I in input and V in output. So here we will have Z in to be low, but Z out should also be low. So this is trans impedance and this is trans conductance, current and voltage. So these are the basic things that we have to keep in our mind before designing our amplifiers,
Mm.
right? Now, based on this information, let's move on and solve the problems. Okay. So
Okay.
today we'll have, yeah, so there are few other names also depending on, while talking about the circuit only, I'll tell you what are the names that I'm talking about. So see, here if you observe the circuit very carefully, this is the forward path, right? This you
Mm.
understand that this is the forward path. And here since the output is being fed, so this is the feedback path. This is
Mm.
the feedback and this is forward path. This is clear to us, right?
Mm. Yeah.
Now, if you see very carefully, your inputs are actually shunted or they are actually parallel.
Yeah.
So here, like if I say I in is actually parallel to this feedback beta times of Ix. This is actually in parallel. So in input side, it is shunt connection,
Mm.
right? But
Yeah.
if you look at the output side, it is actually series connection,
Yeah.
right? So the same current will flow through both the circuits. So it is actually series connection. So when we are trying to write the name of the circuit, we write it as output dash input circuit. So it is actually series shunt circuit or current shunt circuit. So this is output side, this is input side. So that's how this particular circuit, which is given in the problem, is named.
Yeah. Okay.
Okay, so this is the convention that is used. So output dash input.
Okay.
And even here, if you observe very carefully, when we are saying transconductance means current by voltage. So it is
Mm.
also actually output by input.
Yeah.
Transimpedance voltage by current, again output by input. So it is
Okay.
first output then input. So similar way this convention is also followed. So this is called series shunt circuit or current shunt circuit. Clear?
Yeah.
So this is how this circuit is named. Now in this particular circuit, so let's see what are the things which are given. So this circuit is a current amplifier. It has R in, no, I'll simply remove these. So R in of 3 kilo ohms, R out of 4 kilo ohms, AI is 116, beta is 0.25, and yeah, if R out beta is 6 kilo ohms if used, and this is 150 ohms. So these are the things which are actually given to us. Now we'll look into what we have to actually find out in the problem set. So this is the first problem. In this first problem, what we have to do, for the given circuit, we have to find the gain.
Hmm.
So gain, how do we write that? Like I know by IS. So if there was no feedback, what would have been the gain? The same gain that is given AI, which is 116, right? Now
Yeah.
due to this feedback, and we know it is a negative feedback, so what will my new like gain will be? My modified gain will be AI dash. It is actually AI upon 1 plus AI into beta, right? Simply.
Yeah.
Now here observe that we have to use Rn and Rout to be 0 and infinite. So when these are not used, so it is simply like having a beta factor there.
Hmm.
You know? Now we'll also see how this Rn and Rout come into picture and how they actually change the
How can
formula.
we disregard infinite?
Uh, so when we say infinite resistance means open circuit,
Ah, yeah. Okay.
and we say when we say zero, like 0 ohms means it is actually short circuit.
Yeah. Yeah.
So open circuit में तो we can disregard, no?
Yeah. Yeah.
Yeah. So actually it is in parallel. If it was in series, you could not have disregarded that.
Hmm. Yeah.
So that also comes into picture. Like where is it? Because being in series and being in parallel, short circuit and open circuit have different significances. So we have to
Hmm.
keep that in mind. So yeah, here we have simply it is AI dash is AI by 1 plus AI into beta. So how much is it? 116 into 0.25. What will be the value that we'll get?
3.86.
3.86, right? Yeah. This is 3.86. Now moving on to the next problem. So in this problem, the circuit, we have to use the same circuit. Yeah. Screen, my screen went off actually. Okay, yeah. So in this problem, we have to use the same circuit and we have to find the value of input resistance for the current amplifier considering the ideal situation for the same components. So Rn dash. So what will be the value of Rn dash? How will we write Rn dash?
Hmm. There is no
See,
other
we
resistance
have,
there.
yeah, we don't have to consider any other resistance. We
Hmm.
know that there will be a factor of 1 plus A beta coming into picture. This
Mm,
we
yeah.
already know. But we have to think whether it will come in series, or like in multiplication, or is in will it come in division? That is the idea.
I don't know about that.
Okay, you don't have the idea. So what does okay? So let's say um, Arin. So gain. What happened to gain first of all? When we have seen the gain actually reduced, right?
Hmm.
So in case of Rn will also actually reduce.
Hmm.
And when we are talking about R out, so R out will increase.
Okay.
So that is what will happen. So here Rn dash will become Rn upon 1 plus A beta. Simple. So this is what we'll get. Now here we already know Rn is 8 kilo ohms. 1 plus. Now this A, which A we will use? Is it the
Open,
A dash that we have calculated in the previous problem, or is it the A that was
open
given?
loop game. Open loop game.
Open loop gain. So which was given to us. So it is 116 times of 0.35. So how much is the Rn dash that we are getting? The new Rn?
Uh, 266.6.
266.6. No, it should come. Wait. How much is it? 8K or is it 3K? 3K, no? Oh, I've written 3 as 8K. It's not 8, right? It's 3. Yeah, here it is 3K. So it will reduce by that factor. So you'll actually get 100 ohms. 2.66 times it was greater, right?
Yeah.
So reduced by 100. So Rn is actually 100 ohms. Now coming to refer to the same circuit and find the output resistance. So output resistance, as I said, output resistance will, what will happen to the output resistance?
It'll increase.
It will increase. So it will increase by the factor of 8 into beta. So what will happen to the output resistance? It is 4K. So yeah, how much is the output resistance that we are getting?
Mm, 120K.
Yeah, it's 120 kilograms. Okay. Now moving on to next problem. Here again we have to use the same circuit, but now see what has changed. Here we have to use non-ideal feedback network. That means we
So
have to
the
use
R in and R out we calculated earlier was to for the load, right?
uh, no, it was not for the load. So if let's say there is another load, so what will happen is your R out dash will come in parallel to that load. Like where you'll apply your load, you'll apply your load somewhere here, right? It is from here to ground, parallel.
Okay. So the earlier thing we calculated was for an ideal situation.
Yes, it was for an ideal situation. Ideal situation means we didn't had this R in beta and R out beta. Now we'll
Hmm.
have R in beta and R out beta as well.
Okay.
So we have to consider the effect of these two parameters, and we have to find what we have to find is input resistance. So how the input resistance will change? So earlier input resistance reduced by a factor of 1 by A beta. So what do you think what will happen now?
Can you repeat?
So earlier what happened is our Rn actually changed, right? Rn changed to Rn upon 1 plus A beta.
Yeah.
But now we have to consider the effect of R out and Rn beta. So definitely R out beta will come into picture,
Yeah. Yeah.
right? When we are calculating Rn from here, so Zn from here, if we say. So now the thing is how it will change, how our new Rn will change with the introduction of this R out beta. That is
Mm.
the question. So how it will change is, uh, here first of all we'll again have Rn dash as Rn upon 1 plus A beta, but here it is now A double dash. So A dash is the one we calculated earlier, right? It was by the factor of 1 by 1 plus A beta.
Oh, the feedback.
So
Why we?
feedback one. But
Uh,
this is different. Here this when I say A double dash, it actually considers the effect due to this R out. So the resultant A double dash will actually be, so this formula has been derived in the lectures. So when you go through the lectures, so it is there in the lectures. It has been derived very beautifully. So I'm directly writing down the formula. Okay. So
yeah.
it is AI into R out beta upon R out plus Rn beta plus RL. So this is the formula. So since here we don't have RL, we can remove the RL. So we will actually have 116 into R out beta, which is 6 kilo ohms, by R out is 4 kilo ohms, plus R in beta 150 ohms. No, wait, it is, yeah, how much is it that you are getting? A double dash? What is the value of A double dash that you are getting?
Okay, I'm doing it here.
Okay, here it is R out. R out by R out plus R out
4.5.
beta. So it is 4.
4.5.
No, it is, so here it is R in beta, but here it is R out only. So it's not R out beta. So this one is R out and this one is R out beta. So in gain formula, you will get R out and R out, but R in beta. So it is 4K. So we have to see like 4K. It's 116 into 4000 by 4000 plus 150. Yeah. So you must be getting this 9280 by 83.
Okay.
So it is R out by R out plus R in beta plus RL also. I'll write it down for the formula, but since we don't have RL, so we'll neglect that. So this is
Okay.
the formula. Okay. So we'll use this particular game to find the Rn dash. So Rn dash is Rn, that is 3K by 1 plus 9280 by 83 into 0.25. So this will give us a certain value. Now here if you observe carefully, we have not introduced this R out beta factor, right? So if I say Zn, like resultant input impedance, so it is actually Rin dash parallel to R out beta.
Mm.
So whatever factor we are getting over here, we have to use it in parallel with R out beta.
Okay.
So how much is this written bit we are getting? First of all, R in dash we have to find out.
R and dash we found out earlier, right?
R in dash, did we find out? We found out gain, right? A double
Yeah.
dash we found out.
Yeah, yeah.
And that R in dash was different. There it was ideal condition, so we didn't had this effect of uh, R in beta, R out beta, these things. So now, since we have these effects, so the formula of gain will change, and respectively the formulas for the impedances will also change. So maybe you can do the calculations later, or are you doing the calculations? So
Yeah, 1 second.
okay.
It's 103 ohms RN.
Iron is 103 ohms.
Yeah.
Okay. And R in dash parallel to R out, which is 103 ohms parallel to 6 kilo ohms, right?
Hmm.
Yeah. So how much is this setting that we'll get?
101.
101 point something.
Hmm.
So it is around 101 point something ohms. So
Okay.
yeah, this is the setting that we are getting. But this is after introduction of R out beta and R in beta. So non-ideal feedback loop. So now moving on to the next problem. So in this problem again we have to use the same circuit, but we have to find the output impedance.
Hmm.
R out, or I'll write it as Z out. है So in this Z out we'll have the effect of R out and R in beta plus how it changes, like how R out has changed already. So R out will actually become, I'll tell you, or Z out will actually, we'll write it as Z out is R out into 1 plus beta dash AI plus R in beta. Now what is beta dash? So beta dash is actually beta into R out, beta into R out beta upon R out beta plus R out beta plus R in. Yeah. So this is the formula for beta dash and this is the formula for Z out. So with this formula, what is the beta dash that we are getting? It is 0.25 into R out dash is 6k by 6k plus R in is 3k. So it is 1 by 4 into 6 by 9. This is 1 by 3. Oh, wait. It is 1 by 6, right? 1 by 6. So beta dash is 1 by 6. Yes. So this is the beta dash. Okay. So the resultant Z out's formula is R out 4k 1 plus 1 by 6 into AI. So here the AI is the normal open loop gain 116 plus R in beta is 150. So this is what we'll get is output impedance. So how much is the output impedance that we are getting?
42.8K.
42.8K.
Huh?
Isn't it coming 81.5K?
No, it's coming 42. Oh yeah, I put it as 1.1 by 6.
Two one plus 50, 55, yes. No, it's 81.5K.
Yeah, it is 81.5K.
Yeah, 81.5K, right? So moving on to the next problem. Now, okay, so we have come to a new circuit. Now, as we named earlier, can you name the circuit? What is the circuit?
This is transconductance circuit.
Transconductance circuit.
Yeah, yeah. So it is a series shunt.
No.
sh-
See here, what type of connection is this?
Current.
Shunt.
Yeah, yeah,
Shunt, right? And
yeah,
here this is series, right? So
yeah,
it is shunt series
yeah.
or voltage series.
Actually, in my textbook, it is mentioned the other way around.
Oh, but even when we were also studying, and in this lecture also, it is like output then input. It's generally output then input. So output is like here the output is shunt, and here it is series. So shunt series.
No.
Yeah. See, yeah, I understand sometimes, but it is a conventional way. But if you're referring to a certain book, then maybe you can follow that. But
Oh.
so, which book are you using actually?
Microelectronics by Kedra S. Smith.
Okay, Cedar Smith. Cedar Smith is a good book, so I guess it should follow the convention. It doesn't follow the convention. Okay. So maybe you can look into it. But most of the times, even when we were studying, then also the convention was same.
Mm.
And yeah, in these lectures, even sir has used the same convention. So maybe yeah, you can check through once. No? And
Okay.
just in case if you have any doubts, you can look into it. So yeah, for this particular circuit, these are the parameters which have been already given. So let's copy the circuit and we'll move to the problems. So the first problem related to this question is again we have to find the gain. And here since we have to use the ideal voltage amplifier, so what will be the gain? A dash
A by 1 plus A beta.
A by 1 plus A beta. But now here's you look carefully that there is a load.
Mm.
And when we are talking about gain, we are talking about the gain across load, right?
Okay. Yeah.
So if I say that I'm getting a gain of A times V in,
Mm.
this voltage will drop across R out as well as RL and RL, right?
Yeah.
So now what is the factor that RL is actually getting that we need to find out? So
RL is.
see RL, can you see RL over here?
Yeah.
There is a RL in series with R out.
Yeah.
And for now, okay, yeah, R and beta is infinite here. Okay, so since it is now see, you must have observed earlier this was shorted and this resistance was open circuited, right?
Huh. Huh.
But now this is open circuited and this is actually short circuited. Okay, this is actually short circuited. So this, why this has happened, first of all, because voltage and current has changed the terminals, right? Like we have changed the terminal for voltage and current, so correspondingly how resistances will be connected has also changed. So when that has changed, we should also change the open and short circuit concept, because when something is in series you cannot open circuit it,
Mhm.
right? Otherwise it will be completely open circuit.
So for voltage, we can't open circuit it.
Yeah, when it is a Thevenin equivalent circuit, you cannot open circuit it. So here it is in Thevenin equivalent form, right?
Hmm.
So you cannot open circuit it. And when it is in Norton equivalent form, you cannot short circuit it. So that is the thing. So yeah, here this has already been open circuited and this has been short circuited. So we only have the effect due to R out and RL. So now the thing is, gain will be distributed across RL and R out. So how much is it? How much is the gain that we are actually going to get across the load? So let me write it as B. Okay. So the
Okay.
gain that we will get across the load will be AV into RL upon R out plus RL, right?
Yeah.
And due to this closed loop, the actual gain that we will get is B upon 1 plus B into beta. Now A will change to B, this AV, this thing, this AV has changed to B. So
Hmm.
in place of AV, we'll simply substitute B,
Yeah.
right? So here it will be AV into RL upon R out plus RL by 1 plus AV into RL R out plus RL into zero point 0.1. Beta was 0.1. Yes. So first of all, how much is this factor that we are getting? We need to find this. So 175 into RL is 4K by 4 plus 1K. It is 175 into 4 by 10. So B is actually 140. Now when we know, so 140 by 1 plus 140 into 0.1, 140 by 15. So B dash, so the actual gain that we'll have across this circuit is 9.34. Are you getting the same?
Yeah.
है ना? So this is the gain that is after feedback, which will appear across the load. So V out by Vs.
Yeah. Okay.
Clear? Now moving on to the next problem. So in this problem again, we have to find input resistance for the voltage amplifier due to ideal feedback circuit. So input resistance is Zn. Zn will be how much? So here this is voltage source, right?
Yeah.
So we are giving voltage to the input. So voltage में what should be the resistance? Resistance,
Voltage. The source resistance or the input resistance?
input resistance.
It should be high, very high.
It should be high, right? So Zn will actually be Rn 1 times of 1 plus A beta,
Mm. Yeah.
because it is voltage.
Yeah.
For current it goes to division and for voltage it comes to multiplication. That is, we have understood from that thing, right? We want
Yeah.
higher impedance or lower impedance. So now it is 1 plus a beta. But will it be a? So the answer is no, because now we cannot use AV as it is, that is the source gain as it is. We have to
Hmm.
see it across the load, right? So we'll
Hmm.
always use A dash, or maybe B, what we named it, B, right? So we'll always use B over here, because B is the gain that is appearing across the load, and we are talking about uh, that particular load, that is the final gain that we are getting, right? So it is B. So Zn will be Rn times of 1 plus B into beta, that is 2 kilo ohms, 1 plus 140 into zero point 0.1. So that is 2 kilo ohms into 15. So Zn will be 30 kilo ohms, right?
Yeah.
So here, if you observe very carefully, with closed loop gain, the feedback has actually reduced the gain. But if we see the factor of Zn, the Zn should be higher for voltage, right? And after feedback, we are actually getting higher Zn. So it
Yeah.
will further reduce the loading effect. So that we
Yeah.
can clearly observe from here. And if we see its effect, so it depends on actually how your feedback will actually come into picture, whether it will be multiplied, the factor will be multiplied or divided. It actually depends on what type of configuration it is. First of all, whether it is an like input impedance or output impedance, the change will come there. Then secondly, what is the terminal's electrical signal, whether it is voltage or current, because voltage has a different behavior and current has a different behavior. So we have to consider all of those. So when these formulas are actually derived, so they are derived from very basics. We apply KCL, KVL and we will solve it. So
Yeah.
from there only we'll get that. But if you observe the pattern, so it actually differs from what type of configuration it is. First of all, what type of electrical signal you are trying to see, whether it is for voltage or current. Then secondly, whether it is at the input node or output node, that also brings the difference.
Yeah.
Okay. So yeah, so here we have 30 kilo ohms. Moving on to the next problem. Okay. So in this problem, we have to again refer to the same circuit, but we have to find the output resistance. So for output resistance, uh, what are we seeing in the output? What is our output signal across load?
Voltage.
Voltage, right? So for voltage, what should be my Z out?
Less.
It should reduce. So actually, when you'll see, your Z out will become R out
By 1 plus
by 1
AB.
plus A beta times R out. But here it is RL is also there. So RL will also come into picture, right?
Mm.
So if we write the formula, it is actually Z out RL 1 plus A beta parallel to RL. R out 1 plus A beta parallel to RL. So here
Mm.
this AV, here it will come as AV directly parallel to RL. This is one method, or second method we can write it as R out parallel to RL by 1 plus B beta.
Mm.
Makes sense?
Mm.
So we can have either of the two formulas and we'll get the same value for Z out. So here it is 40, 4k by 1 plus 175 into 1 parallel to 4k, and by the other formula we'll have 4k parallel 1k by 1 plus 140 into 0.1. 5 by 5 by 15. Maybe yeah, right. How much is it that we are getting? Yeah, cancel these, no? This actually 5000 by 125. 50, 53, around 53 ohms. Are you getting 53 ohms? You cannot cancel that.
Yeah, 1 second. Yeah.
Yeah, right? We cannot cancel this. Oh, silly mistakes. Okay. So through both the formulas, you are getting 53 ohms, right?
Yeah.
So we can use
So we can use
either of the two. But uh, so once you try to go through the derivation and see like whichever formula you are very comfortable with, so keep that formula in mind. So otherwise you might get confused. So for likewise for Zn also you'll get two set of formulas, and for these also you'll get two set of formulas. But keep in mind only one set of formula which will be like all in one flow, and just in case if you forget also, you if you know the crucial steps of derivation, so you can quickly find out like what is that formula, so you can stick to any one formula and proceed with that. And generally if you are able to remember all the formulas, well and good, otherwise try to relate it with the derivation. So once, just in case if in exam you forget the formula also, but you can take 2 minutes and simply quickly derive like how it is derived. So actually that's why the derivation needs to be done very carefully. And it also tells you how these factors are actually coming into picture. Like what are the paths that we have considered, where all we have applied KCL, KVL, all those things become very clear. So that's why we have to go through the derivation. Okay.
Yeah.
So it has been very beautifully explained in the lectures that are posted right online.
Yeah.
So you can go through. So now coming to this particular problem. So here it is again the non-ideal condition. So for non-ideal condition, we have to find out input resistance with these factors. So the formula for input resistance is, see here also there are two formulas, so I'll only write down the easier one which is easy to understand and remember also. So it is R in 1 plus beta times of A double B, that is B dash. In our case it is B dash plus R out beta. See here R in with some factor will come into picture. plus R out, we know it will come into picture because these two are in series. Now this factor is 1 plus A beta that we know, but actual A across the load is B dash,
Mhm.
right? So that's why the B dash is coming into picture. Okay?
Yeah.
So simply take here 1 plus 0.1 into beta, B dash was, how much was B dash? 9.35. 9.34 plus 1.5 here. Yeah, how much is it? Actually, this beta dash, B dash has also changed because now B dash me we didn't consider the effects due to these R out beta and R in beta, right?
Mhm. Yeah.
Yeah, so this B dash will also change. So that's why this will actually come across around 5.5, 5.5K. But actual answer is 14.5K. So where is it going wrong is actually this B dash that we wrote down now. This B dash didn't had the effect of R out beta and R in beta. We have to consider this that as well. So this will not be the formula. Rn will be same Rn 1 plus beta, but let me write it as A double dash plus R out beta. Now this A double dash actually considers the effect due to R out and load RL. So this AV is AV double dash is actually AV into RL parallel Rn beta upon RL parallel Rn beta plus R out. Yes. So this is actually AV dash, AV double dash. So the gain considering these non-ideal conditions. So this AV double dash will be 175 into 4K parallel 500 ohms 5 4K parallel 500 plus R out is 1K. So how much will it be? 500 is
53.
it 53?
Yeah, 53.8.
53.8. Okay. 700 by hmm. So AV double dash is actually 53.8, right? 53.885. So we have to use actually this name. So once we substitute that, so Rn dash will be Rn 1 plus 0.1 into 53.85 plus this Rn was 2k and 1.5k. 2k 1.5k. So it is 2k into 6.385 plus 1.5k. So how much is the Rn that we are getting? 14.5, around 14.5k you'll get. No? 12, 6, 12 plus 1, 13, and remaining will make as 1.7. So it is around 12.5k, 14.5k. Right? So this is the last problem for today. So using the same circuit, we have to find the output resistance, and the output resistance will be again found out for non-ideal conditions. So for output resistance, let me write this out. So it will be, the formula is R out upon 1 plus beta dash AV parallel to R in beta, this one parallel to RL. So R out by 1 plus beta AV is same, that R out will reduce, that is there, and it will come in parallel to RL and R in beta, that is also we can observe. The only thing that is changing is the factor of beta. It will change, either beta will change because of this non-ideality of R out and R in, or gain will change because of non-idealities. Otherwise, if you observe, the factor remains the same. Here also for Zin, we know that Zin will improve. In case of voltage, the input impedance will improve. And we can clearly observe from here that input impedance has improved, right? So that is this thing. So only thing that is changing is beta or gain, which will change because of these non-idealities. So if we want to write beta dash, so we'll write the beta dash as it is beta into Rn by Rn plus Rs plus R out beta, and AV remains the AV. So first of all, let's find out this beta dash. It is 0.1 into 2k by 2k into, there is no Rs, sorry, there is no Rs in our system, so it is neglected, and 1.5k. So it is 0.2, 0.1 into 2 by 3.5. Instead of 2 by 35. And directly you will have it now. So we'll simply find that out as R out, which is 1k, 1 plus 2 by 35 into 175 parallel to R in beta, which is 500 ohms, parallel to RL 4 kilometers. So this is what we need to find out. See here, if we consider these two, so this is 91, right? 91 ohms, and this is 500 ohms, whereas this is 4000 ohms. So even if we neglect this also, we'll get Z out to be around 77 ohms. And since it is a numerical answer type, so you will get a range for correct answers. So it sits in that range. So it is safe to neglect. See, when there is a parallel combination, so we already know that the smaller value dominates. When there is a series combination, since it is a addition, the largest value will dominate.
Hmm.
So we can simply neglect 4k. So if we neglect the 4k, the z out turns out to be around 77 ohms. And if we solve it till the end, it will come out to be around 75 ohms. So they are close by. Yeah. So what we understood ultimately is the factor of 1 plus a beta will always come into picture, whether it is ideal or non-ideal case. It's just a or beta will be modified because of the non-ideality.
Yeah.
That is the thing. And for voltage, the R out should be less and R in should be high. So with closed loop gain, like with closed loop, we'll always get that advantage. Similarly, opposite for the current, and that advantage also we get through closed loop. But coming to gains, gain always reduces. Whether it is current gain or voltage gain, it will always reduce. But for impedance factor, impedance is actually improved with the open loop gain, closed loop uh, thing. So compared to open loop, closed loop impedances are actually even better. It manages the impedance. Yeah, we are done with the set of questions that were there for today.
Hmm. I had a doubt initially, but can I
Yeah,
share?
yeah. Maybe you can share it now. Should I unshare my screen?
Yeah.
Here is this. Mm, okay. Yeah, it's completely lost. So, yeah, since
Can you
you
see my screen?
no, your screen is not visible.
Okay.
But we'll need my screen also, right, to solve.
Yeah, I'll just show you the problem then.
Okay.
I'm not able to share for some reason.
Mm, share. You are not able to share?
Yeah, can I just copy paste the image in the chat box?
Yeah, sure. Maybe you can do that. So is it like not allowing you to share anything? Is that something of that sort? The problem?
It's not like the share button is there, but it's not being activated.
Oh, okay. There's something new.
It's a simple circuit. Can you just write down the circuit? I just tell.
Oh, okay. Is my
Like,
screen visible? I did share it again. Is it visible?
I don't know.
Okay, wait. Now it should be. It is visible now, right?
Yeah, yeah.
Yeah. Okay, what is the circuit?
It's like a non-inverting terminal is connected to the supply with the resistance
Uh,
in an amplifier, like a op amp,
Op-amp. Okay. So this is your op-amp minus plus. Non-inverting is connected to a resistance.
and a voltage supply.
Resistance and a voltage supply. Okay.
Non-inverting.
Yes, non-inverting. Right?
Yeah.
Okay. What about the inverting terminal?
Yeah, inverting terminal is actually there is a low feedback, negative feedback.
Okay. Oh, okay, okay. It's like non-inverting is connected and inverting is negative feedback with a
Yeah, and there's a
resistance,
resistance.
with a feedback resistance, right?
Yeah, and there's
Yeah.
another resistance parallel to it and grounded.
Another resistance parallel to
The feedback resistance and grounded.
it
Yeah,
must be
something like
like
that.
this, right?
Yeah, yeah.
Yeah, okay.
So,
E naught RF.
so, so yeah, the feedback resistance is given as R2, and the other one, which is connected parallelly to it, is given as R1.
Okay,
And they've given the beta expression, and there's also a load resistance connected in the end.
okay.
Yeah, that's the circuit.
Yes.
And it just changed the notations. I'll tell you what is the expression of beta they have given. They didn't derive it or anything as such.
Okay, what is the expression for beta?
R R1 divided by R2 plus R1.
R2 plus
And
R1. Hmm.
yeah, yeah. Actually, you should write it ulta. Like RF is what you've written. RF is R2 and R2 is R1.
Oh, RF is R2 and this is R1.
Yeah,
Okay, this is it.
yeah, yeah. I don't know
So,
how they got there.
what is the doubt?
I don't know how they got the expression.
Okay, how they got this expression of beta? That is the
Yeah,
concern. All right. Here this is V, right? Voltage V.
yeah. VS RS
Vs, this one
RS.
RS. Okay.
Yeah.
Since there is no other voltage across here, right? Vs. So we'll say that Vs is actually appearing at this point. Okay.
Hmm.
And you know virtual short concept, right? That appears that is
Yeah.
applied for op amp. So
Yeah.
with that virtual short concept, your Vs will also appear here,
Yeah.
right? Here you have V naught.
Hmm.
Okay. So what should we do? Let's write KCL at node Vs. This Vs I'm talking about. Okay.
Okay.
KCL at Vs. So when we'll write KCL at Vs, it is Vs by R1 plus Vs minus V naught by R2.
Yeah.
Will there be any current going in?
No.
No, right? This is 0. So we'll only have two terms equal to 0. Now let's write KCL at V naught also. So when we'll write KCL at V naught, it is V naught by RL plus V naught minus Vs by R2.
R2.
right, equal to 0. When we say gain, it is V naught by Vs. Did they mention anything? Like what is beta? Like,
Beta are like, okay, I'll just read out the question.
huh,
The non-inverting of op-amp configuration shown in the figure provides a direct implementation of the feedback loop.
hmm,
Assume that the op-amp has infinite input resistance and zero output resistance. Find an expression for the feedback factor,
hmm,
and yeah, they give so on. Like, and open loop gain is given as 10 to the power of 4.
hmm. Okay. So it is an ideal op amp. So let's first find out V naught by Vs and let's see what we get. You know?
Hmm.
So V naught by Vs we can find from this expression itself. We need not to go to the next expression, right? So यहाँ से if we see very carefully, Vs is 1 by R1 plus 1 by R2 is equal to V naught upon R2. V naught by Vs is actually R2 1 by R1 plus 1 by R2. So V naught by Vs is R2 R1 plus R2 by R1 into R2. This gets cancelled. So V naught by Vs is R1 plus R2 by R1. This is the gain that we are getting, V naught by Vs.
Hmm.
This is forward gain, right?
Yeah.
So now A beta equal to 1. If A into beta equal to 1, beta becomes 1 by A, right?
Hmm.
And this is A. V naught by Vs is A.
Yeah.
So beta is Vs by V naught. It will be simply 1 by Rn plus Rs. This is what we were looking for, right?
How did you get A beta is equal to 1?
A beta equal to 1, right? So, mm, see, as I was saying, if you give like, if you give whole of your output into input,
Hmm.
then your factor actually, so if it is like, so when I say A into beta equal to 1, that means here it is A and here it is 1 by A.
Hmm.
So which will actually make it as like V in. So यहाँ पे ये A times of V in आएगा. This A times of V in. यहाँ पे it is again V in. So that V in is going into this. So ideally
Hmm.
what I understand is they have got this beta formula from this only. Considering A into beta to be 1.
That is the condition for an
But
oscillator,
that
right?
that's the condition for oscillator.
To get
Hmm.
sustained oscillations.
Yeah, that is Barkhausen criteria.
Hmm.
But hmm. So beta, there, what are they calling beta as? Is it forward loop or feedback path?
Just feedback factor.
Feedback factor. Hmm. Feedback factor. So this is from Cedra Smith.
Yeah, yeah.
Okay. Hmm. Feedback. Okay. See, if we see, this is actually the feedback part, right?
Yeah.
This is actually the feedback part.
Hmm.
So, if I say Vs by V naught will give me my beta, that is feedback factor,
Hmm.
right? So, if I am here and I want to write like, okay, this is V naught, and this is Vs. So, if I write Vs in terms of V naught, so how will I write it? V naught into R1 upon R1 plus R2,
Hmm.
right? Because see, if this is the voltage, so this acts as a series voltage divider, and there is no current flowing into the op amp, right?
Hmm.
So if there is no current flowing into the op amp, then the whole current will flow through R2, will flow through R1 also, and the voltage across R1 is Vs. So I'm writing Vs in terms of V naught. So it will be simply Vs equal to V naught into R1 plus R1, R1 upon R1 plus R2. And when we will say Vs by V naught, which is actually beta, turns out to be R1 upon R1 plus R2.
So that's a given expression Vs by V out is equal to beta.
Feedback factor it is saying, no? So feedback factor मतलब input by output.
Okay.
क्योंकि gain is output by see when we talk about gain is actually output by input,
Hmm.
and feedback factor will be input by output.
Okay.
So ultimately, eh, or ultimately it comes out to be A into beta as one.
Okay.
Yeah, so that's how it turns out. But you should not go by this way. Better you go by this, like Vs
Okay.
by V naught, because it says feedback factor, no?
Hmm.
So we should backtrace it from
Yeah.
V out to input. And generally,
Hmm.
when we are asked for gain, we go from input to output, feedback na output to input. So we'll get that. Right? Is this clear? Any other
Yeah.
doubts?
No.
So this was from Cedar Smith, right?
Yeah.
So maybe in text also they must have used this term as feedback factor beta. You can go through the text once.
Yeah,
Chat.
they did give it a feedback factor, but they didn't like exactly derive or do anything as such
But they
before.
didn't explain like what is it like what is it exactly that they are calling as feedback factor? Did they explain it somewhere? No.
Yeah, feedback factor beta. Find the expression for feedback factor beta.
No, no, that's in the numerical you are talking about, right?
Mhm.
What I'm saying is, in the chapter, did they mention this feedback factor beta somewhere in the chapter, and did they explain?
Yeah, yeah, kind of. Yeah, they did. The same like how you explained earlier. They put the diagram and they explained.
So they explained it like you have to backtrace it and thing like that.
No, not nothing as such.
Nothing as such. So maybe you
Mm.
can look into once because from my understanding, I think what they expected was this, but you can look into the text also once, you know. Okay,
Okay.
what they are actually trying to say when they are saying like what is a beta factor? Uh, do they mean although we are getting the answer that means it must be this thing only, but just to be very sure.
In the textbook, they've given the general diagram you wrote earlier, na?
Ha ha
So from the feedback loop, they have given XF, that is a current or voltage.
ha ha.
So beta is given as XF by XO.
XF by XO.
Yeah.
Ah, same thing, no?
Yeah.
XF by XO means ultimately XF is the voltage at that point, Vs point, and
Mm.
XO is the output voltage, right? If I'm not wrong.
Yeah.
Ah, yeah, so same thing. They mean the same thing. So
Yeah.
it's input by output.
Okay.
And ultimately, if you see, it actually comes as A beta to be 1, although that is Barkhausen criteria, but yeah, here it also satisfies.
Mm.
Any other doubts?
No, none.
No doubts? So, did you understand what we discussed today? Any
Yeah.
doubts in the problems that we did?
I know.
So, in case of like doubts in the formula, or just in case you feel like how these complicated formulas are actually coming into picture. See, 1 plus a beta thing we all understand how it comes. But when it is non-ideal, that is the case where it becomes a little tricky, because beta is changing, gain is also changing with these non-ideal factors. So there we can maybe look into like how these factors are actually being introduced into the formula. So
Hmm.
for that you can follow the lectures which
Yeah.
are posted, right? Okay, so are you taking the exam, online exam for this course?
No, I actually registered for another exam. I'm an electronics student.
Okay,
I just took it.
acha, okay. So no, actually why I'm asking is I just wanted to know the exam date. Do you know the examination date for this
It's
particular
29th of this month.
29th of this month? Okay.
Hmm.
So we are left with one more week, like one more set of problems, which will consider few more like problems coming next week. So I was thinking whether like anybody will be there or not. So yeah,
Hmm.
29th is the scheduled date. No, today it's 17th.
Hmm.
So we'll have the lecture on 24th, 25th.
You study in IIT Madras, right? I'm sorry,
No,
right.
Gandhinagar.
IIT Gandhinagar.
Yes.
Did you go in through GATE?
Yeah, I have qualified GATE and I was a early admit student. So I
Oh,
got it on merit basis plus GATE. So yeah.
I actually wanted to ask a little about GATE if you don't mind.
Yeah, sure, please go ahead.
Like, what is the like out of eight? If I've heard almost like 80,000 people all over India like write GATE.
Hmm.
So how many people actually qualify GATE out of that? Like,
So it actually depends on the cutoff marks that they set up, and mm,
no, I know the passing mark, but
uh,
just like how much?
uh, 8,000 maybe, 7,000,
8,000.
8,000, yeah, or even like 6,000, 7,000 तो होगा. 6,000,
Hmm.
7,000 students qualified.
Hmm.
Yeah.
How easy is it? Like, I'm not.
Okay,
It's not
so
easy.
if we are saying talking about easy, so the thing is, if you want to score 100%, then it is difficult. But
Hmm.
if you want to qualify, it's easy. If you want to qualify, you don't have to go through rigorous practice or anything. It's mostly based on whatever we study in college, but
Hmm.
it's just that we need to practice, brush up those basics and all. So qualifying is okay, easy only. It's not like it's too tough, you have to do rigorous studies and all. You just need to revise your notes, then you can simply qualify. But yeah, if you want to have like a score which is for ranks under 100, 200, then you'll need rigorous practice, because that is where actually the difference comes. When
Hmm.
you want to score higher, each and every question, so you cannot leave any question just because it is going to like it is difficult or you are not able to attempt it. That should not be the case, because you have to score 100, or like you have to at least attempt 100%. Then you will have few incorrects, and as you know there is minus marking. So you have to
Hmm.
go through minus marking and all, and then you will land up somewhere, right? So but you have to aim for 100%. If you want to go for ranks, say uh, less than 200 or 100, then you should go for 100%. So there you need to practice, because always in every exam there are set of difficult, moderate and easy questions. That is all, like it is general practice in all types of basic competitive exams. So most of them are general and moderate. There are few questions which are actually difficult ones, and which actually decide for the students who are going for higher, like better ranks, like AIR ranks within 50, hundreds. So they basically don't leave any question. So yeah, that is the case. But for just qualifying, it's not that difficult. Like you can go through your notes, you can practice
Is
normal
it worth it if
problems.
I just qualify? No, no, right?
No, because see, for PhD, it's a different game. For PhD, you don't need very high scores. If you qualify, you'll get a better stipend, and the things are different for PhDs. But if you want to go for masters, you should at least have less than 500 for better IITs. And even for top IITs, NITs, you better have like top IITs basically, IITs, ISC, you better have less than 100. Yeah,
Hmm.
that is the case. Because I guess you want to go for masters. Is it your game?
Yeah, yeah. Actually, I've heard that, education is basically funded by the government in Germany if I actually submit my GATE course.
Oh,
So I was
okay.
aiming there.
Yeah. So, like, for the starting, you should first brush up all your basics, like for basically all the subjects, and then you can go for like you can try on for difficult problems.
Which was a difficult subject, like of all.
Difficult subject of all. Actually, there were few subjects that I didn't touch. I just left them, but I guess EMT would be the difficult for people, maybe. EM wave, like electromagnetic
Electromagnetic
wave.
theory. Yeah, okay.
Yeah, that might be a little like integrations and all, it's too much. Otherwise, maths is like, okay, matrices, determinants, basically these things, and you'll have differential equations.
Mhm.
Then networks, you will have few problems on networks, few problems on analog op amps. What else do we had? Actually, it's been 3 years,
Mhm.
so I barely remember. But yeah, what else? What is signals? You will have few problems. Signals basics, you will have the problems. Then a little advanced also you'll have problems. Digital, you will have one or two problems. Like basic digital. And or
Mhm.
not gate sort of like basic latch flip flop, those basic
Mhm.
digital problems you will have. What are the other subjects that we have, like basic common subjects? Did I miss any subject? mm, yeah, more or less it's like this, but yeah, I remember analog there were questions based on op amps. EMT, like electromagnetics, there were few questions. Signals, there were question. Networks, there were questions. Maths, there was questions based on matrix and dates, differential equations, those problems. Yeah, more or less. Did I miss any major subject, or if you remember any subject?
No, no.
No, right? Or you can go through previous year problems so you can have a certain idea like, okay, which are like major key subjects. But sometimes, okay, but yeah, it will actually give you a certain idea about what type of questions are asked, what is the pattern, like
Mm.
how deep actually you have to go into the subject, those sort of things. You can
Yeah.
look into through previous year problems. That will help. Anything else? So GATE is done, right? GATE exams GATE exams are over, no? Did you
Yeah, yeah,
appear?
this year. I'm in second year, so I couldn't appear.
Oh, you are in second year. So
Yeah,
next year you can appear, right?
yeah, yeah.
But till then, will you be done with all major subjects of yours?
No, no, I'm just gonna attempt.
Hmm.
That's it.
But majorly you will be done, I guess, in third year. Third year, नहीं, एक semester बस होगा ना? So,
Mm.
but major subjects you will be done, I guess. Networks,
Mm.
EMT, OPAMs as you are studying, so OPAMs are also done.
Mm.
Maths must have been done. So basic subjects are big because advanced subjects may say like computer architecture or machine learning, AI. These are the advanced subjects that we take up on, right? In coming like in the coming semesters or towards the end. You go for image processing, signal processing. But
Yeah.
those subjects, so basically, GATE is not for too advanced subjects. It's more about the basic subjects. So what we study in first, second year, or even till you appear for your GATE, right next year, whatever
Mm.
subjects you'll be doing, it must be sufficient. You'll
Mm.
cover almost all the subjects. So,
Mm.
yeah. So basically,
Yeah.
try and finish the course because I think like most of the syllabus all over India for all the universities is more or less the same, and it is the same as GATE syllabus also. So you can check through the GATE syllabus.
Yeah.
So
Yeah.
it will be more or less same. So whatever you are being taught in the college, you can brush up those and you can go through them properly. So I guess it will be done. At least uh, you can qualify and have a clear idea, like okay, how it is going. And because you will have another attempt, so you can even brush up on like difficult topics or the topics that you left, you can go through. So there's it.
Mm.
Two
Yeah.
attempts are possible, no? Third
Yeah.
year
Yeah.
and fourth year, at least you can get. Mm, yeah.
Yeah.
All the
Thank you.
best. Yeah, all the best. So we'll be having one more session next week, and
Mm.
I am not sure if I have to, but maybe I can have one more session after that for summarizing also. So if you want to join, you
Mm.
can join.
Yeah. Yeah. Sure.
Yeah. So I was
Thank
just
you.
looking at the problems what we are going to do next week. It's again like feedback amplifiers only. So we'll be going through these problems. But those are different type of problems. So we'll touch upon this one
Yeah.
next week, same time.
Yeah. Yeah.
Okay. Thank
Bye.
you for joining. Bye. Enjoy your day.